So, do you guys remember when we learned about tangents when we were doing SOHCAHTOA? The opposite over hypotenuse, adjacent over hypotenuse, right? The tangent was the opposite over the adjacent when we were talking about functions, right? We have that on the board over there. When we're talking about a tangent to a circle, it is very different. It's the same word, but it means something different in the context of circles. Alright, so don't confuse the tangent in this unit with tangent in the unit 7 with the right triangles. It means something different. So a tangent for a circle is a line or segment that touches a circle once. And that once is the key word there for the definition of tangent. If you want to draw a little illustration of what a tangent is, you can draw a little circle here, and then you can draw a line like this, and then draw a point like that. So that line or segment that you drew, where it just barely touches the circle, but it only touches in exactly one spot, that is a tangent, okay? The point of tangency is, I'm sure you guys can obviously figure it out, the point where a tangent meets a circle. Oops, that's an F. Tangent meets a circle. So the point of tangency is that one exact point where the tangent actually touches the circle. That's why it's called the point of tangency. Okay, so this vocabulary, I'm kind of bringing that in together with the vocabulary that we talked about last time. Remember how last lesson we started that with a section of vocabulary? So what I want to do before we have two rules that we're going to learn about for a tangent. A tangent does two really cool things. We're going to learn about those two theorems and how to use them to solve. But before we get there, I just want to do an overall review of all the vocabulary that we've learned up until now. Like the minor arcs and the major arcs and the center, the radius, the diameter, everything that we learned last time, in addition to tangent and point of tangency. So, looking at this picture is what this little section is based off of. I want you to name what each of those things would be called, okay, using vocabulary. So if we're first looking at point D right here, what would be the geometric name for this point right here?
Point D.
Now, it has a special name in the context of this picture. Like, look
Right
at point
angle.
D. It's a point.
Tangent.
It's a point.
No.
Tangent. Is it tangent?
Guys, a tangent is a line or a segment, therefore a point cannot be a tangent.
Point of tangent.
It's a point of tangency.
The point of intersection.
You guys see do you see how this right here is just barely touching the circle, this line right here? Where does it actually meet the circle?
At the line.
No, this line, where does it touch the circle?
At the bottom.
Right there. Point D. So this is called a point of tangency.
I said that.
Everybody kept saying it's a tangent, it's a tangent.
I thought
It
someone
is
said
the
it's a
point of
tangerine.
tangency. So if a tangent touches a circle, the point where it does that is called a point of tangency. Alright, next we're going to look at line FH, which is this one right here. Oops. Well, we can actually trace it, you guys can see. FH is right here.
Tangent.
Okay? It is a tangent. We're going to specify a type of tangent. So you guys see how there are two circles right here? And it's going on the inside of them. This is called a interior tangent. It is a tangent because it only touches these circles in exactly one spot each. So it touches the circle at H, it touches the circle at F, so 1 point each. It's going on the inside of both of them. So that's why we call it an interior tangent. What about point C? That's another very special point. What would I call this point, point C? And in
The middle.
context to this circle right here.
Oh, I know. It's the medium.
Nope. What do you call the point right here?
Bisect.
Center. You learned that yesterday. I mean, not in last class. The point at the center of a circle is called the center.
No.
Okay? So point C is referred to as a center. Alright, AD is from here to here. What do I call this? From one edge of the circle through the center to the other?
Diameter.
The diameter.
Yeah.
Diameter.
Again, something we talked about last time. Then CD, that's from the center out to the edge. Center out is called a radius.
Radius. Yeah, exactly.
Notice, I just want to make a quick point. Notice how the CD and AD are segments. You guys see how the symbol changed? This one had arrows, these don't. Right? That's why they're diameter and radius, they're segments. Now I'm going to switch to DE. Again, that's a line this time. So DE, what would I call this?
Exterior.
An exterior tangent. Again, this is only touching the circle at one point each at D, and then in the circle it's only touching it at E. And it's on the outside of the two circles, not in between on the outside. So we're going to call that one an exterior tangent. And then lastly, I have angle ACH. We have a special name for an angle that looks like that, position-wise. Central angle. Any angle that comes from the center of a circle is called a central angle. And again, I made sure that you guys know it's important to know that kind of angle because there's going to be another type of angle that we're going to learn day 4 maybe? I can't remember. That's another type of angle called an inscribed angle. And you guys are probably going to have trouble remembering the difference between the two. So as long as you guys can remember now what a central angle looks like, you'll be better prepared. Right, so don't forget that vocabulary exists and that I do expect you guys to be able to identify those kinds of things. Now separate from this, I don't have it written down, but I'm just going to do a quick quiz for you guys. How would I classify arc AH?
Repeat that, please.
How would I classify what kind of arc is arc AH? Okay, what about arc AD?
Diameter.
Semi what? Semicircle.
Huh?
What about
Oh.
arc BD? What about arc BDH? That'd be major. What's the main difference in how you name a minor arc versus a major arc? Minor has
Two.
two.
Major has three.
Major has 3. What about for a semicircle?
Half a circle.
How do you name it? How many letters do you use for a semicircle?
2.
2. Again, at each endpoint. Alright, so that was just a quick recap of the vocabulary and the notation that we use. Alright, now we're going to talk about the 2 theorems that we know about a tangent to a circle. So the first one here, a line is a tangent to a circle if and only if, so that means it's a biconditional. Remember the double arrow we learned in Unit 2? If that line is perpendicular to the radius or diameter, depending on which is drawn, at the point of tangency. So the tangent to a circle is going to be perpendicular to the radius or diameter, depending on what's drawn, at the point of tangency. Now this is a biconditional, so it works both ways. You could have it be a tangent first and therefore conclude that you have that perpendicular relationship. Or you could have a perpendicular relationship first and then conclude that you have a tangent to a circle. Okay? So this is how you can draw this picture. Oops. Go ahead and draw either a diameter or a radius, and then you're going to make a little 90-degree angle right there. This is what the theorem is talking about. If you have a diameter, a full diameter, or just a radius, again, it depends on what they've drawn, when they meet at the point of tangency, which is right here, they're going to create a 90-degree angle. The tangent and the radius / diameter are 90 degrees. Okay? So one way that you guys could use this, again, it is a biconditional. So this kind of question right here, if it asks you if a tangent is being shown, this is using the P arrow Q direction of this biconditional. It's going to say, if we start with Q, what you want to do is check to see if there is a perpendicular relationship at the point of tangency. If Q is happening, then P is true, then it's a tangent. So we're going to be using this rule in reverse to see if these are tangents. So in order to tell if this, well, hold on, which one of these am I suggesting could possibly be a tangent? The 8, the 17, or the 15? 15. We're trying to speculate if this guy right here is a tangent or not. What would need to be true for that to be a tangent? Where? There would need to be a right angle right here, right? There isn't one right now, but we need to figure out if there is one. How do you guys think I would verify if there is a 90-degree angle right there? Do you see a shape anywhere in this picture? Triangle. Have we learned about how to determine if a triangle is a right triangle or not? Pythagorean theorem. So we're going to be bringing back that stuff from Unit 7 about the right triangles. To confirm if this is a tangent or not, we're basically going to check to see, is this a right triangle? That's what we're going to ask ourselves. And the way we're going to figure that out is by using Pythagorean theorem. So which one of these sides would we kind of imagine is C? The 17. Remember the hypotenuse, or the longest side is C. So what you want to do is you want to take 15 squared plus 8 squared, and you want to see if that's equal to 17 squared. If it is, that means this was a right triangle. You have a right angle, therefore it was a tangent. If it's not, then it wasn't a tangent. So you guys have your calculators. If we do 15 squared plus 8 squared, we get 287. What is 17 squared? I'm sorry, I don't know why I said 7. 289. And we also have 289 over here. So they're equal to each other. So was this a right triangle? So can I put this little right angle right there? So is this a tangent? Yes. This is a thought process you go through to check to see if something is a tangent or not. You kind of imagine that this is a triangle and you try to see if it's going to be a right triangle. So same thing in this picture. Which one of these segments am I conjecturing is a tangent? Not 4. Only this one. We're trying to see if this is a tangent, okay? So if that's going to be a tangent, what relationship needs to exist? Jackson? Well, I mean, what kind of relationship am I looking for with the circle? The tangent should have what relationship with the... Okay, so we're trying to see if this guy right here is a right angle, and we would be able to do that by using the Pythagorean theorem. Now there's a small problem.
What's the problem?
I'm wondering if you guys can see. Here, I'm going to draw the triangle over here for you guys. And I want you to help me see what the problem is. Okay, what's this? What's this? What's this? No. Two is this, the radius.
Oh, it's just like, 4 is, actually no, 5 is the
Why? Why? 2 is isn't every radius supposed to be equal in a circle? Okay. This 4 is only talking about the point out. Isn't the hypotenuse this entire thing though? So I need to know what that is. It's also 2 because that's also a radius. So then what's the entire side here? 6. You have to make sure you guys are paying attention to what's going on in the picture. Everybody follow? Sometimes they'll swing a radius around and you have to use that other radius to help you as well. So now that we have these numbers, now you can use those to check to see if it is a right triangle. So 2 squared plus 5 squared. Does that equal 6 squared? No, it does not. Therefore, would this be a tangent? No, because that wasn't a 90-degree angle. We just confirmed it wasn't 90 degrees. So that wouldn't be a tangent. Right? This is just one way of using this formula, or sorry, this rule, this theorem, to help you solve using a tangent. So you can verify if something is a tangent or not in the first place. Now, the second rule that we're going to learn here and then practice here. Okay? I like to refer to, some people call this the clown hat rule or the ice cream cone rule. It's very simple. So 2 tangent segments to a circle. Excuse me, hold on.
Coronavirus.
Sorry. Okay. From a common exterior point, so that's going to go here.
I can't see. Blurry.
So 2 tangent segments to a circle from a common exterior point are congruent to each other. This is not one tangent, this is kind of like 2 tangents working together. So what this means, I have the picture over here that's illustrating this. So these are the tangents. This is tangent number 1, this is tangent number 2. Here's your common point, your common exterior point. They have to be coming from the same point on the outside. So if you have 2 tangents coming from the same point out to meet your circle, these 2 are congruent to each other. And so I like to call it the clown hat rule, because it's like a hat on top of the circle.
Can I get back in this thing?
I don't know, because the clowns have like a party hat, whatever, I don't know.
No.
It's a hat. Alright, so if you imagine kind of a hat sitting on top of your circle, if there are 2 tangents, the 2 tangents that make up the sides of the hat are going to be congruent to each other. Does that make sense? Alright, so let's see how we can actually use this to help us solve. So these circles down here. Alright, so for this one right here, I have a 4-sided figure, quadrilateral. I'm trying to find this angle right here, the y, and then this angle right here, the x. Okay, so finding the value of the variable, we're going to assume that all lines that appear to be tangents are tangents. So in the directions, it's allowing you to assume that if it looks like a tangent, it is. If you guys don't see that permission in the directions to make that assumption, you can't make that assumption. Alright, so I have this tangent right here. What can you guys tell me about this intersection right here? Oops. The tangent with the radius. It's a right angle. Remember that's what our first theorem said? A tangent when it intersects with a radius or a diameter, it's 90 degrees. So what does that mean about this angle that I have right here, x? What's the measure of angle x? 90. That's just using theorem number 1. So the corner that's created where a tangent touches a radius or a diameter is 90 degrees. Okay, so I can draw that in right here. Right. Now, the only other thing I'm looking for is y, which is a central angle. I'm going to try to find y. Now, the only information that we know about central angles right now is that it's equal to the arc, but I don't know what the arc is. Okay? So I'm going to do something a little bit different. You guys remember last unit with 4-sided figures? What do all the angles inside of a 4-sided figure add up to?
90.
360. Okay? So right now I have 90, I have 70, and I need to find this one. Do I know what the other angle is over here?
Yes.
That one's also 90, right?
360 minus.
Now I wasn't looking for that one, but I need to know what that is, right? So I have 90, 70, and 90, and I'm trying to find y now.
360 minus
250 minus
So you're going to take what these add up to,
250. Right.
which is,
250.
and you're going to subtract them,
What pen?
and that's going to give you the measure of the angle. Now, quick question for you guys. This one was 110. We just found that. What's the relationship between 110 and the angle across from it?
7. Yeah, equals 1.
They equal 180, don't they? Keep that in mind.
Oh, that's what we could.
Okay? If I'm now trying to find this angle right here, I'm going to call this one x again. Alright? How do I find that angle? How did we do that over there?
180 minus 65.
165 minus 180. Right.
No, how did we do it over here?
You just
Find
they
the
were
side angle.
I find these two,
Yeah.
right? Oops,
90.
sorry. 90 and 90 makes 180, right? And then what do all of them add up to?
360, so we add a 65.
So we're going to add up these three and subtract from 360.
245.
That's 245.
115.
Okay.
Comment on math.
So then, okay. So then I ask again, what's the relationship between this angle and that one? Do you think that's always going to be the case?
Yeah.
Why would that always be the case?
because it's just how it works.
Like,
Well, I'm not talking about situations other than tangent. I'm just talking about if you have two tangents that are intersecting the circle like this, and you draw two radii to complete that figure, why would these always be supplementary? Because these two angles, didn't we say that these two are always going to be 90? Right? These two are always going to be 90, so you have a consistent 180 already taken care of. And if all the angles inside add up to 360 and you already have 180 taken care of, then the other two always have to add to 180 as well. Okay? So a shortcut, you guys can definitely do that every time if you want to. Find the two 90s, add them with this angle, and then do all of that minus 360, or 360 minus all of that, the angle measures that you know already. Or you could just automatically say those are supplementary and get it faster. Okay? So that's one thing you can do with those. Alright, now we're going to switch from angles and work with the clown hat rule. Okay? So this is a tangent, and this is a tangent coming from the same exterior point. So what would the length of x be? 78. Very simple. They're just equal to each other. What about y? Now y is not a tangent. Be careful, y is not a tangent. What would I call y? A radius. Do I have another radius in here?
Yes. 62.
So y would be equal to
62.
because all radii are going to be equal to each other. Okay?
Interesting.
So, pretty straightforward using the clown hat rule. It's pretty easy to use. Same thing here. I have a tangent here. I have a tangent here. They're coming to the same exterior point, and I'm trying to solve for x. So what kind of equation could I write? X plus 20 equals? Right. Because the two sides of the clown hat are equal to each other. So you just write an equation, and then we're going to solve. Pretty simple algebra, you get 16. Right? Alright, so everybody see how we did those few? Kind of warm up a little bit. Alright, these ones are also going to be the clown hat rule. They look intimidating, but they're actually quite simple. Okay? So these ones we're going to find the perimeter of these shapes by using the clown hat rule. Alright, we're going to assume lines that appear to be tangents are tangents. Alright, again, they've given us permission. Jackson. Jackson.
Wait, boy.
Alright, so let's look at this picture right here. The little arrow thingies, the brackets here, are telling us that the entire length is that number. So just keep track of that information. Alright, if you guys have color coding, you can different colors, you can use that to help color code. Otherwise, I'm just going to show you how you can do this. It's really helpful. So I have one hat right here. Does everybody agree that's one hat where the two tangents meet? That's one. I have another one right here. It's a totally different hat on that side of the circle. I have one here. And I have one here. Sorry, can't really, that's the same color as the picture, but whatever. So you guys see how I have 4 different little sections? All of those pieces that are the same color are equal to each other. So we're just going to go through and find all the missing information. Let's start with the blue hat. If I know that this is 11, what is this piece?
11.
Also 11. Right? Very straightforward to get that one. Now, to keep going around the circle, and you can go whatever direction you guys want, but I'm going to keep going around this direction. This bracket is saying that all the way from here to here is 20.5. Well, if I know this piece is 11, then what's this piece of it? 9.5. Just using some subtraction, because it's, again, it gave us the whole length and then part of it, so I use subtraction to find the other part. Alright, well if I said this was 9.5, what's this?
9.5.
Also 9.5. Then we run into a number that I know already, 8.6.
8.6.
So if this is 8.6, what's this one?
8.6.
And then we run into another scenario with a bracket.
15.
So the whole thing is 15. No. This bracket is saying that from here to here is 15.
Oh, okay.
This part is 8.6.
So you subtract that by 15?
So you have to use subtraction. So if the whole thing is 15 and then I know just the upper part is 8.6, what would the lower part be? 6.4. And then the last segment I don't know,
6.4.
6.4. So then to find the perimeter, you're just going to take each of those little pieces, go all the way around, add them together, and you get the perimeter.
Wait, when? So that means the side with the green and the red equals the side of the brown and the blue?
No, the full lengths of all the sides are different.
Oh, okay.
All you're doing is finding each of the little halves of the
The
hats
hat.
as you go around, and then you can add them together. Does anybody have the total? 71. Alright? So again, the application of the clown hat rule is not hard. You just have to remember when and how to use it. Alright, let's try again. I'm going to use my colors. So I have 1 hat, 2 hat, red hat. Ha! Good job. Alright. So let's go ahead and be smart about where you guys need to begin the process. Which hat do you think I would start with? Or does it matter? Doesn't really matter. But which one would you start with?
The blue one.
The blue one? Okay. I know this is 13.
The other side's 13.
So this is 13 right here. Alright, what would the next hat be that I could work with?
And that's the half of that, then the green side is 13. too.
Nope. 13 start and stop it right there. What about the red hat? This one's 10.3.
And the other side's 10.3.
So this is also 10.3.
And you
Then on the
subtract that
bottom, it's a bracket.
by 20.
So it's saying the whole thing is 20.7. So if this part is 10.3 and the whole thing is 20.7, what's that little piece?
10.4.
Which means that this piece
10.4.
is also 10.4. So again, once you have all the little pieces kind of chopped up and you find each of them individually, all you have to do is add them together to get the perimeter. Yep. 67.4. Alright, I'm going to let you guys try this one by yourself, see if you can get that number. So again, use your color coding if it's helpful. Chop up the little pieces and add them together. Give you a second to see if you can figure that out. It's not 71. Should be 70.8 is what you had. We should have 9.9s here. Should have 9.7s here. 5.8 and 10 and 10. Those are each of the little segments that you guys should have. Alright? So that's the extent of the clown hat rule, what you guys would be expected to do with that. Our main focus that we're going to switch to for the end of class is using the first rule, the relationship with the radius and the tangent. But this is the context in which you guys would use the clown hat rule. Or just straight up like we saw on the other page where I just have 2 tangents and you guys have them equal to each other. Okay? Any questions about that before we move on? Alright. So these last questions that we have here, we're going to be going back to theorem number 1, which said that a radius or a diameter is perpendicular to a tangent at the point of tangency. So again, we're going to be focusing on finding the segment lengths. We're going to assume that lines which appear to be tangents are tangents, and we can use decimals instead of simplified radicals in this problem set. I'm allowing us to use decimals for this one. Alright, so taking a look here, which one of these would be considered a tangent? 7.5, okay. Now, when it comes down here to the point of tangency, this right here is a diameter, correct? What's the relationship where they touch? A right angle. So what shape am I working with? What kind of triangle? A right triangle. So we're going to use stuff that we've learned in the past about right triangles to help us solve. Now, what's interesting about this question is that I have x right here. What is x referring to? Okay, but in order to create the triangle, I need a diameter, right? So I'm going to need to adjust the picture just a teeny bit. I'm not going to rotate it now. I am going to redraw the triangle over here. I'm going to redraw it, but I still need you guys to tell me a little bit more about the picture in order to label the triangle. So now this is 7.5, right? This side right here, 7.5. We know this side there. They gave me the bracket saying that the entire thing is 12.5, so that's nice. But how would I label the bottom? We said this was a radius, right? How many radii make up a diameter? So if one radius is x, then the full thing is 2x, which is what Oliver has been saying. But yeah, it's 2x. So you guys need to be really careful when you see a missing piece. If you see something that's empty, you better fill it before you start solving the problem. Because if you're working with a triangle that isn't actually labeled correctly or fully, then you're not going to get the right number. All right, so all this is, it just becomes Pythagorean theorem. You guys know how to do Pythagorean theorem, right? So we're just taking stuff that we already know how to do and applying it here. So which one of these would be C?
12.5.
Okay, so that means I have 7.5 squared plus 2x squared. I'm going to put that in parentheses. Equals 12.5 squared. 7.5 squared, let's find that as a number. Oops. 56.25. Now, I did put parentheses around this on purpose. Remember, when you guys are squaring something that has two parts, you guys remember everything needs to get squared? So what does this become when I square it? 4x squared. So it's important you guys remember to put the parentheses around that if you have two parts, just like we saw before with numbers that had like 2 root 3. Remember we had parentheses around that so we could distribute. Same thing with something that has like a variable and a coefficient. And then 12.5 squared. Okay? So that becomes pretty simple to solve from here. You guys just need to subtract. Right? We're going to subtract the 56.25, which I believe just leaves us with 100, right? And then you divide by 4.
That's a lot.
What?
Yeah.
156.25. That's 12.5 squared. And then you divide by 4, becomes 20. Nope, 25. Sorry. And then you take the square root. 5. You get x equals 5. There you go.
Are we ever going to have to do the thing when you're saying you got 2 on the square root? You're looking at 2 in the square root.
You're I'm allowing the use of decimals. So no. In this scenario, I am allowing the use of decimals for argument's sake. Alright, so really what we're doing is we're just boiling down the information to a right triangle. Try again here. Which one of these segments are we going to conjecture as a tangent? X. Oops. And then it's coming to meet the radius here at a 90-degree angle, right? So this blue shape right here is the shape we're going to be working with, the right triangle. So I'm going to come over here and redraw it. I highly recommend you redraw it off to the side so you're forced to think about what numbers you would put where. Okay? So x goes up here. Right, what does this d equals 30 mean? Diameter is 30, right? But I've said that this piece right here of the triangle that we're using is really what?
The radius.
The radius, which would be 15. So again, be smart about how you're working with the picture. Then how does the 8 come into play?
C.
Would I just call this whole thing 8?
Or,
We have another radius right here. Remember how we did that? We had an example on the first page where we did something like that. If you guys are kind of swinging another radius around, it needs to join this little section. The 8 is only talking about what's outside of the circle. So you'd have to add them together. The radius plus the 8. 23? What? Okay. So 8 is, no, because you're thinking about the clown hat rule. The 8 doesn't count as a tangent because it's going to cut through and touch the circle twice. So the 8 is not a tangent. You can't use the clown hat rule. Alright, so once you get the triangle all set up with all the numbers everywhere, it's just as simple as Pythagorean theorem. Okay, which one of these is our C?
15.
Nope. 23 is the C. So we're going to do 15 squared plus x squared equals 23 squared. I'm just going to go ahead and subtract those in my calculator. So whatever those numbers are squared, when you subtract them, you get 304. And then again, in the directions, I'm giving you permission, even though we're using Pythagorean theorem, and I would typically expect a simplified radical whenever you guys are using Pythagorean theorem. The directions want the answer as a decimal. So all I have to do is take the square root of 304 and tell me what that is. Let's say 1 decimal point.
77.4.
There you go. Okay? So again, you have to be very, very careful. Move very carefully and methodically as you're going through these ones. Alright, next one. Which am I going to say is the tangent?
The tangent is 20.
Okay? Then I have my radius right here. What happens when the radius meets the tangent?
It becomes.
Alright, so I have a right triangle over
I
here.
was gonna say, they just beat me too.
Okay? So what's this side up here? 12. This side right here? 20. And then again, be very careful. This x that we're looking for is only the part outside of the circle.
It'd be
X plus 12. If the radius was 12, which they told us here, the other radius is also 12. So to get the full length, I have to add those pieces together. It's 12 plus x. I know you guys are tempted when you see two things, you just glue them together. But don't call it 12x. They have to be added together. 12 plus x. Alright, so this, I'm actually going to have you guys do a special strategy for this one. If you guys try... Now, you could do it this way. Are you guys comfortable with factoring?
oh,
Okay, well guess what? You don't have to.
I don't
So-
know how to.
This question is designed for factoring, but I have a way that you guys can avoid that if you would prefer to not factor. You guys have to be equally careful about remembering the strategy though, okay? So this, whenever you guys have a side here that has an addition, like x plus 12 or x plus 2 or whatever it is, if you guys have something like this, what I want you to do is I want you to, instead of using that expression, I want you to just call it y. Instead, leave that there, like don't completely get rid of it, but just maybe draw a slight slash through it and call it y instead. Because that'll help us solve for x by using y. So if I treat this as y and I find what the whole length is, if I know what y is, I can just subtract 12 to get x. If I can find the full length and then subtract the 12, that's how I get x. Okay? So that's what I'm going to do. I'm just going to find the full length all at once, and then I can use that to help me solve for x. So when I do Pythagorean theorem, it's going to be 12 squared plus 20 squared equals y squared instead of the x plus 12. It's a handy way to avoid the factoring. So then I get 12 squared plus...
144 plus 20.
Okay, so that's 544. And then I take the square root of that. Okay, so I've determined that y is equal to 23.3. What was y referring to again?
X plus 12.
X plus 12. So if we're saying that y is equal to x plus 12,
X equals
I can swap out the y for x plus 12, right?
So X would equal 11.4.
Oh, I like this strategy.
You would subtract 12. You would subtract 12 to get the x. So that's 11.3. Okay, so if you don't want to take the factoring route, turn that expression into a new variable y, solve for that, and then you can use subtraction to find the value of x. Okay, does that make sense? So try using that instead of factoring. That will help. Alright, we got 3 more just to get this to sink in a little bit. A little bit more before we leave. Alright. Which one of these guys is supposed to be my tangent?
14.
Okay. Which one of these sides is supposed to be perpendicular to the tangent?
Simple
What?
I mean, yeah, because it's a right angle.
Not only is it important for you guys to remember that that relationship exists, you also need to know where the right angle should go in the triangle. I'm going to come over here and redraw it. Alright, what numbers go where?
I don't know.
What would this be?
14.
Okay. What would this be?
10.5.
What would the hypotenuse be?
X.
X times 2.
2x
2x.
X
plus 10.
plus 10.5. Because this segment is made up of the little piece on the outside of the circle and another radius.
So then you know what? Cross it out. Put y.
So again, just here's what you guys want to do. Whenever you see a blank piece, you need to find what that is. Usually the blank piece is in another radius. So if you already know one, you know the other one's going to be the same length. Yes.
What if you have like 2 blank pieces? Like, what if you don't know what the radius is?
They have to give you that.
Yeah.
Yes.
Okay, but what if, like, so like say they gave us x, but they didn't give us any radius.
They won't do that, don't worry. Alright, so again, this is the one, another situation where a piece or a side of my triangle has addition. So this is another one where we're going to use that strategy. Any side that you have, if it has a variable plus a number, just turn it to a y and solve for it that way. So we're going to do another Pythagorean theorem, so 14 squared plus 10.5 squared equals y squared. Because that's the hypotenuse. Okay? I'm going to find those numbers. 306.25. Then you're going to take the square root of that. 0.5. Oops, that is 17.5. Okay? That's what y is. Now how do I find x?
Equals x plus 10.5.
Right, you swap out, since we know that these are representing the same thing, I can swap out the y for what it was representing, the 10 plus, or sorry, the x plus 10.5,
Minus 10.5.
and then you just subtract it.
Equals 7.
7.
Don't forget to do that swap at the end. Put it back with the expression for y. Okay? Alright, we got 2 more. Sit up, Jason. Don't be distracted.
I'm ready. I'm ready to check.
Come on, let's go.
I got this.
Alright, which one is
15.
the tangent?
And then x is, yeah, see, no, this was what I was talking about. Like, what if it gives us 17 and then.
But you were asking what if it gives you this but not that,
Oh,
right?
yeah.
So it's slightly different, right? But therein lies the right triangle, or the right angle for the right triangle, and then I'm going to draw it off to the side. Oops.
So the radius would be 8.5.
You don't know that. You don't know if it's being divided in half. Can't assume
What
that.
is this the diameter?
Alright. I don't know the diameter.
Well, no, alright, fine. Okay.
So I know this piece is x and this piece is 15. What's this one?
17.
17. That's what the bracket is for. The little arrows are telling you that the entire length is 17. We don't know how it's being split up. We just know the whole thing's 17. So this one's just a really straightforward Pythagorean theorem. So x squared plus 15 squared equals 17. So how did I know that 17 was the c, by the way?
Because it tells you.
How do I know it's the longest one?
Because it's bigger than 15 and it's obviously bigger than that.
How do you know?
By looking at it.
Well, maybe the picture's drawn weird.
How can a picture be drawn weird?
I don't know. I'm looking for a different answer. How do you guys know which side is the longest?
Because the brackets is saying.
Across from the 90-degree angle
Hypotenuse.
is how you figure that out. Right? The hypotenuse is across from the 90-degree angle. That's how you know it's the hypotenuse. Okay?
Yes, I do.
Alright, so then what's x?
8.
8.
Excuse me.
Okay? Alright, this last one's a little bit weird. Jason, which one's the tangent?
6.
No.
What?
Wait,
It's
what?
5.
Oh, yeah, 5. Whoops.
The tangent does have to be outside of the circle, everybody. So this is our tangent. This is what's going to meet the tangent to create a 90-degree angle.
X plus 3. Booyah, baby.
So I have 5 here. What is this right here? This long
6.
other leg? No. Do I have a missing piece?
Yes.
Right
It's
there.
not marked.
So you can find it. This is another 6. A radius is going to be equal. Every radius is equal, so this is 12. Again, if you guys see a missing piece, you better figure out what it is. And then what's this?
X.
What's the expression?
Yeah, wouldn't it be 15?
X plus 3.
X plus
Yes, sir.
3. Alright? And then remember, anytime that you guys have a side that has 2 pieces added together where one of them is a variable, we can call that y instead and use that little trick. So it's going to be 12 squared plus 5 squared equals y squared.
160
So then y is equal to
13.
13. And then remember to do that swap. Y is equal to what?
X plus 3.
X plus 3.
So X equals 10.
X equals
Alright, I'm going home.
X equals 10.
I'm going home too.
It was a fun class.
No, it wasn't.